into some of these examples. And so the first one we're going to start with today is called flow control.c. So go ahead and find that or follow along. So this file just contains a bunch of very basic examples for how to do if-else. So there's also this concept of switch statements within C and C++. I think it's in a lot of languages actually, but we're not really going to talk about switch statements. That's another form of kind of flow control that you'll often hear discussed in intro to programming courses, but we won't really bother getting into that in this course. So we're just going to focus on if-else here, and so I'm again assuming that everyone is pretty familiar and comfortable with this kind of logic. The idea is it allows you to conditionally execute some command based on some criterion that you provide. And so in a very simple example, here we're just saying if, and within an if statement in C, we surround what's actually being evaluated in parentheses. Okay, so this is what's being evaluated. This is what's being tested. And in this case, we're just including the value of a variable. So this might look a little strange to you. And we generally don't do it this way, but I've set it up this way because it helps demonstrate what's actually going on, how C is actually treating these statements. So within C, there's not really a native Boolean type. So you can't set a variable, like there's no bool type that you can set to true or false. So instead, when you're evaluating these conditions, anything that is non-zero evaluates to true. Anything that evaluates to zero evaluates to false. Okay, so in this example, and that includes even negative numbers. So here we're starting out by setting I, or declaring and initializing I to a value of 1. And then when that evaluates, it should print this. So let's go ahead and build this example, typing make. And that builds everything, all 10 or so of our examples. And then to execute it, we're going to type / flow control and enter. Okay, so don't worry about the last 3 lines for now. The first 3 things that are printed, though, pertain to kind of this block right here. So these first 3 print statements. So what this kind of demonstrates is that this is evaluating to true, and therefore printing this statement for all 3 values of I here. So when I is 1, when it's 123, when it's even negative 321, that's evaluating to true, and it's printing this statement right here. Okay, so that's kind of what we expected based on my explanation. The next thing we do is set I equal to 0, and now we introduce kind of an else condition. So here, if whatever this expression is evaluates to true inside of the parentheses, then we'll execute this block of code. Otherwise, we're gonna execute this block of code instead. And so in this case, I is equal to 0, and that is literally the only thing that I can be in order for this not to evaluate to true. So as a result, this block, it's going to jump into the else block, and it's going to print I as false with a value of 0. And that's indeed what we see down here below. Does that make sense to everyone, how that works? It's pretty straightforward. So you can also include multiple sort of conditions here. And so now we're introducing these and or operators. Again, I'm assuming people are familiar with this from other languages. The and operator within C is 2 ampersand symbols in a row. Okay, and the or operator is just two vertical bars in a row. So the vertical bar on my Mac keyboard is just a shift, and then the backslash gives me the vertical bar. Okay, so now we're, like, as an example, here we're saying if I is greater than 0 and y is equal to 26, then this is going to print. So both of these have to be true in order for this condition to be printed. And since I is equal to 0 at this point, we do not expect this condition 1 to be met. And when we come down here, it's not met, so that's good. The other thing to note here is that we've also used this equality operator. So this tests whether a certain variable has a given value. A very common mistake when people are first using C is rather than the equality operator, they use the equal operator. And so kind of the issue with that is that, well, there's kind of a big issue with it, is that will run, actually, because that's a legitimate command or a legitimate statement within C, y equals to 26. But it can lead to, it's actually not doing what you expect it to do. And anytime you just assign the value of a variable in this way, you end up getting a output that is equal to, I think it's equal just to 26 in this case. Let's test that really quick. I'm a little fuzzy on this. So if I do a printf, testing, and I'm going to print a val of expression is, and I'm going to do %d for an integer, and I'm just going to type here y equals 26. See what happens. Okay. So I might get a warning when I build this. I don't even get a warning, actually. And if I run it, the output is testing val of expression is 26. So it essentially just prints the value that we're assigning in this case, which is not, this is not what we want. We want this to evaluate to 0 if they're not equal, and we want to evaluate to 1 if they are equal. So that's something that can be a little dangerous and can lead to some pretty nasty bugs if you're not careful. Just make sure you use the equality operator here. All right, moving on, the next block is an if-else statement, or an else-if statement. So if you want to have just a single block where the first if statement is executed and then each is executed in sequence, and you break that into an if followed by an else-if, 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 and then the else, the last kind of condition is just like a miscellaneous, like a catch-all. Like if none of these conditions were met, then do this. Okay, so notice that around each we have to include these open and closed brackets. You can also you'll see this done differently. You can break these brackets off to the next line. Some people will do it like that. Some people will break it off to the next line for functions. For if-else statements, we'll do it in this way. You can also, I believe within C, just get rid of the brackets if you're only executing a single line of code within your block. Okay, so you can do it like this if you prefer to have that indentation, or you can execute it like that. So to test this, I'm going to make yes, cool. So it built and it executed. So you definitely need the curly brackets if you have more than 2 lines inside of the block. Otherwise, it's your choice. You can include the brackets, or you cannot. So it's just kind of a matter of style and preference. Let's see. So finally, you can also have nested if-else blocks. And so we can, we can ask if y is equal to 26. We enter into this block, and then within the block, we have a separate if-else block. So the not equal. So we've seen the equality operator. This is the not equal operator. If I is not equal to 0, then print I is not equal to 0. Else print I is 0. Okay. Does that all make sense? Okay. Cool. Well, let's move on to loops. So you will find that in loops.c. So there are a couple of different flavors, actually 3 different flavors of loops within C. For the most part, 4 loops are the most widely used, they're the most common. So I think within the class we'll mostly just be dealing with 4 loops. If you're coming from Python, you're probably used to loops that look quite a bit different. So within Python, let's see here. You're generally looping over a list or something, some form of list. Let's call loops.py. So, my list equals something like that, and we can do a my list.append and start appending values and go crazy. .append to, and then kind of the syntax you use for a for loop in Python is for list val in my list. That's sort of the preferred way to handle loops within Python. And you can print list val, something like that, right? So there's a couple differences here. In Python's pretty unique in that it uses tabs or spaces for different levels of code blocks, whereas C uses the curly braces. But let's go ahead and save that, and we will run it. .py. There we go. It just prints the 2 values that we appended to the loop. And so within Python, you generally have you're essentially assigning the value of each element in your list to some variable. And it's done in a little more readable way. Within older languages, it's more based on, you just iterate based on some count. So you have some sort of counter that's generally an integer, and then you just increment that counter to some value. Okay, so let's say that we are going to be dealing with kind of array sizes of 10 in this example. So my loop size in this first for loop is just going to be equal to 10, and we're assigning that to n. And the way a for loop works is that it starts by initializing the value of the index. So our index here is I. And so we're initializing that value to 0. And then we execute this block, so whatever's inside the loop gets executed. And then we perform the last bit here, so the bit after the second semicolon, the I++, which, is anyone unfamiliar with that, I++? It's just incrementing the value of I by 1. And so it's the same thing. So I++, let's do it in a comment. I++ is the same as writing I equals I plus 1. So we're just incrementing the value of I by 1, and then we're testing a condition. If the condition is true, we execute another block of the code. We execute the next iteration of the for loop. If it's false, then we jump out of the loop and the loop's over. Okay, so that's the pattern. You start with initializing the value, and this is only executed once, the first time you enter the loop. You then execute what's inside the block here. You then perform some sort of increment here, and this doesn't have to be I++. It could be I minus minus. You could decrement the value of I. You could, you could change I by some other expression. So you could increase I by 2 or 3 or 4. It doesn't have to be just by 1, but this is the most common thing that you'll see. Kind of a for loop in its most simple form. Right. Does that make sense to everyone how that works? So let's play with this. already built here. So if I execute loops, we scroll up. Oh man, it's crappy. Let's do this. Comment these out real quick. All right. I'm going to remake it, re-execute it. Okay, it's easier to read. So now we're just setting x based on the value of I times 10, and then we're printing that value out. So nothing too earth-shattering going on here inside the loop. Some of the interesting things, though, to try are, what do you think will happen if we do this? Predictions on what will be printed. Correct. Because it's starting with that. It initializes, and before it does any sort of testing or incrementing, it immediately executes a block of the code. So that can be a kind of surprising feature sometimes. Oops, did I lie to you guys? Is this some other language I'm thinking of? Yeah, I think I just lied to you guys. I'm sorry. All right, yes, I lied. I'm sorry. So, so I guess the order is it initialized tests, executes the block, then increments, then tests. And so it does do a test after that initial. I was thinking for some reason it didn't do a test initially. So that might give you, that's probably behavior that you would more expect. It's a little more intuitive, I would say. Okay. So that's a for loop. That's the most common type of loop that we'll see. There's also a while loop. And so a while loop, in most cases, can just be expressed as a for loop. But there are certain situations where it just makes a little more sense. It's a little cleaner to do something as a while loop. So with a while loop, you're only evaluating some expression and then testing the value of that expression. And then within the actual while loop is where you have to actually do your increment. And so here we're just testing the value of y, and assuming that that is not true, then we are executing what's inside the block and then coming up and testing again. So this is a case where you can easily end up inside an infinite loop if you forget to like increment your counter or something like that. Print that out. A little easier to read. No, that's okay. All right, so now we're just going by 12s. And notice that we do make it to 108, and as soon as we do, when we test this condition, it's no longer true, so we jump out of the while loop. There's also a do while loop, and the only difference with the do while loop is that we always execute what's inside the code block before testing. So this can sometimes make more sense if you don't want to test that condition initially. If you always want to ensure that your code block is executed at least a single time, is when you would end up using a do while. That. Alrighty. Okay, cool. So pretty much the identical output there. So that's all I got for loops. Are there any questions at all about any of that? Okay. Any questions from the remote folk? Okay. Well, let's move on to pointers, which is one of the more challenging topics within C if you've never seen them before. So to do this, I'm going to start out and let's kind of back up and talk a little more conceptually about what pointers are. So the way I always like to explain pointers, pointers think of variables as objects with the following attributes. And so when I say objects, I'm sort of implying like an object within programming that contains a bundle of data and sometimes methods associated with those data. So in this case, I think it's helpful to think of pointer as, to think of variables within C as not just a value. It's actually a little more than a value. So the first thing it is a value. It contains some value. But it also contains, and this is something we talked about yesterday, is a type. So each variable has some sort of type. It could be an integer, it could be a single precision floating number, double precision, a character, and so on. And the last attribute related to a variable is a memory address. Okay. Hex. So the memory address is expressed as a hexadecimal number. And so if anyone's unfamiliar with hexadecimal numbers, it's like a base 16 system. So we're used to seeing everything in base 10. Hexadecimal, all it is base 16, and so it goes all the way up from 0 to 9 like we're used to. But then once it gets to 9, rather than starting over and beginning to add that second digit, it keeps going all the way to 16. And so, or I guess 15 if you start at 0. And so the way that that's traditionally done is with letters. And so once you get past 9, the next character is an A, and then B, then C, D, E, and I think it stops at F. So that's all it is, and it's really commonly used when you're doing some sort of binary operations. So it shows up a lot within like low-level memory addressing and that sort of things where you're dealing with bytes and bits of information. Things get expressed as hexadecimal numbers. And so when we print this stuff out, it's going to show up with a bunch of numbers and characters, and it's going to look confusing and scary. But don't let that scare you. It's just, and you can think of it as another number. It's just the address that maps to the location of where this value is stored. Okay, so does everyone have this? Actually, let's do this. Okay, so let's illustrate this with an example. So let's say we have a variable I equal to, oh, why am I doing it like this? Hold on, I'm being stupid. So let's say we have I equals to 2 in our C code. Well, what that, if we think about this variable as a, gosh, it didn't turn out how I thought it would. Okay, there we go. It's like an object with a couple of different attributes. I really need that pen to show up a little thicker. Try this. Let's just keep going. So the value here is equal to 2. Type is an int. And then finally, we're going to have some sort of attribute here, or some sort of memory address. So I'm just going to use an arbitrary digit here. And so when you see hexadecimal numbers represented, it always uses this notation 0x. And so anything that begins with a 0x, you know, is a hexadecimal number. It's usually corresponds to a memory address of some sort. Okay, so that would be one example. With a pointer, this is the first time you'll have seen this, is we can write something like this. Man, I know that probably looks super odd, but I will explain it shortly. Okay, so now the value equals 0x, 1, 2, ... type equals address of int. So here, this is the one that we really need to focus on. But let me go ahead and fill in this last one. Address equals 0x34. Okay. So on the left, it's pretty intuitive. It's an integer, it's a value of 2, and it has this address. With a pointer, the value of a pointer is an address. So it's actually, its value, not just its location in memory, but its value contains a memory address. And so in this case, we have written I space asterisk I pointer. So the name of our pointer variable is I pointer equals ampersand I. And what that ampersand does within C is it points to the address of some variable. And so we've already declared I over here, and I should have, should have done this. Really? There we go. So over here, I is an integer. And within this expression right here, we are assigning I pointer the value of the address of I, which is why it has the same, its value corresponds to the address of I. It's essentially what we've done here. And then it has its own address. A pointer is a normal variable, just like any other variable, so it also has an address, but it's in a separate location. So it has its own independent memory location. And inside that memory location, it stores the value of another variable's address. So if we were to kind of map this out, if we thought about each one of these little squares that I'm about to put in here as a memory location, so if we called that a memory location, and that, so you might call this 0.11, 0x12, 0x13, 0x14, 5, 0x16. Okay, so each one of these little blocks represent a memory location. So in the case of I, it's stored in memory location 1, 2. And so the value of I is stored within that location. And we also have a pointer that's actually pointing to that address. That wasn't half bad, was it? Okay, so if we think of iPointer, this is what iPointer is doing. It's just pointing at that memory location that also contains the value of I. And so iPointer is also going to be in its own little memory location. So I've given it 0, or I've given it a memory location of 3, 4 right here. But it could just as easily be somewhere like right here. And then within that unit of memory, it would contain the value that it's pointing to, the memory address.
So if your variable was named int x, would it be x pointer then?
So the name of, so you can call the name of the pointer anything you want. Kind of the convention, just for clarity, is to give it a name like iPointer, or like the name of the variable followed by PTR, just to make it clear, to be explicit that it's pointing to it. But this could be anything. This could be Y, this could be J, it could be my super awesome variable. Yeah, so it can be anything.
The asterisk, why do you have to give it asterisk?
Right, so the asterisk is what actually denotes, that's how you declare a pointer. So, so it would be incorrect to say like int iPointer equals ampersand I. That would give you a compiler error because you'd be trying to assign the value of an integer to an address. But when you put this star here between the type and the variable name, it tells the compiler this is a pointer type, so it's going to be storing the value of some address. So yeah, that kind of leads into my next point. Actually, let me leave some of that there. I'm just going to get rid of this down here. Okay. So putting ampersand in front of the variable returns address of variable. Putting between type and variable name declares that variable as a pointer. And the last point is that this is one that we haven't seen yet. Putting an asterisk in front of a pointer variable. So after we've already declared our pointer and we've assigned it some value, we can put a star in front of that pointer variable to get back the value that it's actually pointing to. So if you put it's called dereferencing a pointer. Putting a star in front of a pointer variable returns the value in the address that pointer is pointing to. So we'll see that in an example coming up. So this is kind of the funky syntax that you have to get used to. Right, so the star, just remember you need that star when you're declaring your pointer, just to tell the compiler this is a pointer type. You need the ampersand to actually get the address. And then eventually we'll use a star as well. So for instance, if we had this variable, if we had already declared this variable iPointer, and down here I wrote something like printf iPointer, well, it's pointer d that would print a value of 2. Okay, so we've already declared it. What we're saying here is we want to access the address space that iPointer is pointing to. So that's how we get back that value if we need to use it. So let's look at an example of this. So pointers.c. I think my session kind of stalled here. Yeah, let me restart this. Okay, so let's look at pointers.c. So what we're doing here is we are, it's pretty similar to the example we just saw actually. We're starting out by just declaring and assigning a value of 1 to an integer called I. And then we're going to declare a pointer with the star character. So in this case, we're just declaring it. In the notes that I just drew, we were declaring it and initializing it in one step. But here we're actually going to declare it initially. And then down here, we're going to assign it the address so that it's pointing to the address that's storing the value of I. All right, and then we're going to stop, and we're going to print out some memory information. So if you actually want to print the memory location, the special symbol is P. So you use a $P, and we're going to pass ampersand I. So that means give me the address where I is stored. And then we're also going to go ahead and do it for I pointer just to convince ourselves that it gives us back the exact same memory address. And then we're going to go ahead and take a look at the memory address of the pointer itself, which should be different. And then finally, we will dereference the pointer to get the value that it's pointing to. So let me type make, and I'm going to run that pointers. All right. So if we just kind of look through this one line at a time, the first thing that's being printed here is the memory address of I. Okay, and so that shows up in the first line of our output down here. So the 0 followed by an X and then an S or a 7FFD23BCCC4C is the memory address expressed in hexadecimal of the variable I. We then print the value of I pointer, and notice that we don't put an ampersand in front of it. We're just passing I pointer itself. And so it should give us back a memory address because that's what a pointer is. That's what it stores. And that is, and so it's actually giving us back the exact same memory address, which is what we expect, right? And then we're going to print the memory address of the variable itself, the pointer itself. And so this is actually slightly different. If you'll notice, that last digit is a 0 instead of a C. So it's a slightly different memory address than the one that it's actually pointed to, which makes sense. Okay. Any questions about that at all, about those memory addresses? Still kind of conceptual at this point. So in practice, what you usually want to do is, if you're wanting to modify the value that a pointer is pointing to, that's where you get into dereferencing. And so here we're going to point the value, we're going to print the value of I, and then we're also going to print the dereferenced value of I pointer. And remember, when we do this syntax, the star I pointer for a pointer, that's just, it's going to print the value that's stored in the memory address that I pointer is pointing, that the pointer is pointing to. And because I pointer is pointing at I's memory address, we would expect this to print the exact same thing. And that's what we see. So I is equal to 1, and the dereferenced I pointer is also equal to 1. Finally, if we can actually modify the value that I is pointing to. And so this might seem kind of odd, like rather than, we could just as easily do this by updating the value of I, but instead, to convince ourselves that they're actually accessing the same memory, we're going to dereference I pointer. I keep pointing at the monitor. We're going to dereference I pointer and assign that a new value, and then print the value of the dereference pointer as well as the value of I. And what we see resulting from that is that the value of I is now changed. So we we never actually reassigned the value of I. We did it indirectly by modifying the value in the address space that I pointer was pointing to. It's probably, I know it's probably a little hard to wrap your mind around at this point. So just to kind of illustrate a little bit further what's going on here, are there any questions before I do that? Are people thoroughly confused? It takes a little bit of time to kind of get used to it. Yeah, right. So let's say that we created another variable. Yeah, question.
So how would you delete the pointer so it doesn't point to that?
Yeah, so to do that, so for those online, the question was, how do you delete the pointer, like so that it's not pointing to anything anymore? So what you would do is something like I pointer equals null. Like it's called a null pointer. It's not. It's set up. But it's not pointing to anything. It's not storing any useful information.
And just getting rid of variables in general, necessarily here or that.
So we'll talk. This will come up a little bit later. I think probably tomorrow when we talk about dynamically allocated arrays. So far, everything that we've generated is on something called the stack, so that you don't need to actually manually free it up. But tomorrow, when we start dynamically allocating stuff, then yeah, you'll have to free up the memory so that like the operating system can reclaim it. So let's try this. Here's a little test. Make sure I get this right. All right. So let's say we had another variable called j, and we set j equal to I. And now we come down here, and at the very end of our program, we're going to do a printf j equal to %d. What do you guys think the value of j will be at the end of the program? So we just, all we've done is, it says, so he guesses 2. So there's pretty much 2 options here, and 2 is one of them. So who thinks, let's take a vote. Who thinks the value is 2? Okay, we got 3 hands in here. Becca, do you think it's 1 or 2?
I think it's 1.
Okay, Becca's going to say 1. Have any explanation?
Because I don't think that changing the value of I updates the value of j.
Yeah, and that turns out to be correct. So if we think about it in terms of our, I already deleted it. Essentially, when we do this, when we're assigning the value of j to I, we're doing that in a completely separate memory space. And so if we think about like this little horizontal grid that I had before, maybe it'd be useful to go ahead and do this again. Let's do. So if we have a little grid representing where variables are stored. Okay, so I might be right here. Once we declare it, it sets aside that memory space for I. But when we set up j, it's going to be in a completely separate memory space. So it's going to be maybe somewhere over here. And then we have our pointer, which is going to be pointing, oh, that was poor. It's going to be pointing to this memory space. That's an arrow. It's like the worst arrow ever. I apologize. So this is I pointer, and we're updating the value stored in this memory address, but that's not going to touch this memory address at all. So it's not going to affect the value of j. So if we make that, did I already make it? Print pointers. Guess I didn't save it. Yeah, so j is equal to 1. So j is equal to its initial value. It's never actually being changed. All right. So any other questions before we move on? If you don't, if you feel like you're sort of understanding it, that's definitely a win. If you feel like you don't 100% get it quite yet or appreciate what's going on, that's all right. These will pop up a little bit more in the next few examples. Just remember that when you hear pointer, think memory address. It's pointing to memory and allows you to point directly to memory. And where this ends up being really important is when we are writing functions and we want to pass a variable to a function as an argument and actually update the value of that variable so that it's updated within the actual memory address, so that after that function it has that updated value.
So you can assign like two arrays together. Array 1 equals array 2. Within Python, if you do that, it's like shared.
Yeah.
So it's separate.
So that'll come up. We'll talk about that because arrays and pointers are intimately linked. So that'll definitely come up. I'll get to that later. All right. So let's move on. Let's see if we can at least get a start on the functions.c code. This is another really important one. Okay, so this example is a little more lengthy. Within a C program, if it's all within a single file, when you're defining a function, those functions need to be defined before they're called within the file. And so my main function here is going to be at the very bottom of the file, and then I'm going to be calling functions that I've defined above main within this file. All right, so there's kind of a lot going on here, so I'm going to kind of step through one piece at a time. So let's start in our main function. We first just declare and initialize two different variables. One's an integer, one's a float. And then we declare another float, and we assign that the value that is going to be returned from a function called mySimpleFunctByValue. All right, so I'm assuming most people here are familiar with functions from other languages, but we have this function defined above. So to call that function, you just write the name of it, followed by parentheses, and then any arguments that that function accepts. And so if we scroll up to the actual function definition, it's the very first one. So it's this block right here. Okay, so recall from when we talked about the main function yesterday, is that the type out in front is what's going to be returned by the function. So this function is going to return a single precision floating point number, followed by a space of the name of the function, and then we have to include the arguments that are going to be passed to this function. So for each argument, you have to include the type as well as a sort of a dummy name for that variable. And so a good practice is to use a different name for the variable than the one you're passing. So here we're going to call it iloc and xloc. Loc kind of denotes local. So these are two local copies of the values of I and x that we're passing in from the main function. And so the function itself isn't really doing anything very exciting. It's just going to update the value of iloc and xloc. One interesting bit here, though, is that we are doing something called typecasting here. So if you want to perform an operation on mixed types, you'll have to kind of update the type. You'll have to typecast one of those types. And so in this case, we want to multiply iloc and xloc together. One's an integer and one's a float. So if we want to assign a new float, the way to do that is to typecast iloc, which is the integer, to a float. And so we just open and close parens and the type within that parentheses to do that. And then we're going to return the value of xloc, so the product of those two numbers is going to be returned back to our main function. Okay, so I think that is it. So let's go ahead and look at the output of that first function. Okay, so the first thing that is printed, we're not actually not printing anything from there, are we? No. So the first thing that is printed is that the value of I, x, and y after we've just called that first function. So here we see that I is 22, X is 234.23, and Y is the product of those two. So is there anything surprising or any comments about those variables at all? In particular, I and X. Are those the values that you'd expect to see?
There's 3 extra zeros for the flip.
Right, there's some extra zeros. But something that might be a little surprising is that the values of I and X have not changed. If you go back into the function, you'll remember that we're passing I and X, and those are represented by these different variable names here, and we're actually updating their values. So they're being updated in this function, but when we jump back out of the function, these variables don't have those updated values. They just have the variables from the original assignment right here. So that's one way to do it. So one way is to make them global to the entire scope of the program. If possible, you want to avoid doing that. The way to update them is, so what we've done here is something called pass by value. And when you pass a variable by value, it's actually creating a copy of that variable and storing it in a separate memory location. Okay, so iloc and xloc are in completely different memory locations, and so when they get updated, that doesn't touch the original values of I and X at all. If you actually want to update the values of I and X, that's possible. You have to pass them by reference instead. So pass by value versus pass by reference is a really important concept in C. Actually, let's pause and just stop here since we're about out of time. So tomorrow we will kind of revisit pass by value, and then I'll introduce pass by reference. But just conceptually, the idea is to pass the address of that variable, and then within the function, you dereference that pointer, update the value that's stored at that address, and then when you jump out of that function, you'll have the updated value. Okay. Any lingering, burning questions before we go? No? Okay, great. Thanks, everybody. I'll see you all tomorrow.